Hey everyone, Mr. Olson here, just trying to get you up to speed on these topics that we're adding to our list of things to know for prerequisite skills. So this is topic 1.2, analyzing graphs of functions. There are definitely some key ideas in here that we will be using in calculus all year, so I want to just highlight those. A lot of this stuff should be things you know very well, but there are a few points that I just want to highlight. So obviously the graph of a function, we've all been graphing things for years. We know what f of x terminology is. We know that if we say f of 3, we mean evaluate the function's vertical value at that point where x equals 3. So you would be wise to just kind of flip through this section in the book just to process it at your own speed. But knowing the domain and range of a function is important. We have 4 ways to understand functions: verbally, graphically, equations, and charts. You want to be sort of familiar with what that means in terms of the allowed inputs. That's the domain. I love it. 2 words, allowed inputs, and then the resulting outputs for the range. So here you can see the domain. It looks like we are allowed to put in from -1 up to 5, but not including 5. So here is the way we can use interval notation there, where the hard bracket means we can include -1, and the softer parentheses means we get up to but do not include 5. Similarly, the range, the outputs, go from -3 up to +3, and they include both of those points, so we have the hard brackets at both ends. So know those basics about range and domain and how we use interval notation. Okay, so vertical line test, wonderfully visual, very good way of thinking of functions. Functions are things that pass the vertical line test, as we have seen in one of our previous class videos. Okay, so I will not highlight that. Zeros of a function in math, I think it's hilarious that there are things that are so important we give them lots of names. So zeros, our roots, our x-intercepts, okay? So 3 different ways of talking about the same thing. There they use an x-intercept, but you'll see that they don't use the term roots there. But when we talk about like rational roots, we're really talking about rational zeros. There are some fine point distinctions, but for our purposes, really very similar concepts. So we find zeros by factoring and looking at each of the factors, setting them equal to 0, so on and so forth. I won't go into those techniques, but you should definitely know what those are. Okay, now increasing and decreasing. Calculus is wonderful at finding out where things increase and decrease. Simple visual graph. It's as the words imply. Think of like a stock market. Stock market is going down, it's decreasing. It holds steady, we call that constant, and then it's increasing. All right, so finding out when functions are increasing or decreasing is important. We will use interval notation to describe that. So this, you could see, we would say it would be a hard bracket at -2 going up to 0. It is not increasing or it is not decreasing. Well, at the endpoints, things are not increasing and decreasing at endpoints. So those would be soft parentheses in all these cases. A single individual point cannot be increasing or decreasing. Looking at these, here again, more examples of increasing and decreasing. I think you have done this in prior years, so it should not be too new. Relative minimum and relative maximum, sometimes called local minimum and local maximum. It just means that when you're at a point and you go to either side of that point, if it is less, then we'd call that a relative maximum. This point looks like it's an absolute maximum. There's nothing higher than this, but still, because on either side of it, it's going, it's a value below that, we would say that's also a relative maximum. Plural for maximum is maxima, so don't get psyched out by that. So there are the 2 relative minima, and again, graphically, it's quite easy. Approximating a relative minimum, that's not a key skill for you guys. Linear functions, so graphing lines should be rock solid. Writing linear functions, definitely rock solid skill. That's in our placement test for freshman year, should be solid on that. Things get more complicated when they're chopped up and they're piecewise. step functions, so you may want to look at that. Think of it as like a children's book where they've got people segmented by top half, middle half, bottom half. We take functions and we can just take various functions, slice them up vertically, piece them together, piecewise defined functions. The things get interesting when we're looking at, okay, this is a function that's going up. It goes up and it includes the point 1 comma 5, then drops down. So what's going on at that break, at that gap? That's where we will talk about continuity and things like that. Then definitely know the concept of even and odd functions. It's actually quite simple visually. Even functions, think y equals x squared, x to the second power. It's all about the degree in our original sort of understanding of polynomial functions. But it's not only polynomials that are even and odd. The sine curve and the cosine curve. The sine curve is an odd function and the cosine curve is an even function. Why is it? Because we're looking at really just a way of describing mathematically the symmetry to the x-axis versus symmetry to the origin. Odd functions, you put a thumbtack in the origin and you can twist it 180 degrees and it's the same thing. Think of a cubic function. Even functions, think of a parabola going through the origin. It's symmetric about the y-axis. You can flip it vertically, fold it over, and it's the same thing. Okay, so mathematically, do know these mathematical proofs for even and odd. They're quite simple. You just want to plug in an x and plug in a negative x. If you get the same result coming out of your function, you're good to go. It's even. Here you plug in a negative x and then you plug in a positive x and you see if the two functions are equal when you change the f of x function into being a flipped upside down negative version of that. All right, so there's an example here where let's see, they work through it. Actually, right here are these sort of the two examples that you can look through. Okay, so that is it for 1.2. Hope that makes some things fairly clear.